All right, welcome back to our flipped chemistry classroom. And today we begin with our discussion of thermodynamics. And specifically today, we are going to be talking about heat and transfer of heat. And we're specifically going to be talking about something called specific heat. And we're going to be talking about ways that we can calculate energy changes. So just a quick review, we remember the law of conservation of energy tells us that energy cannot be created nor destroyed, but it can be converted between forms and it can be transferred between different objects. And so when we talk about the change in energy of a system, there are two different ways that that energy can be converted. It can be converted into heat that is flowing into or out of the system. And remember, the system is the things that we are looking at, we are focused on frequently. It is a chemical reaction. So the sign of Q is going to be negative if the thermal energy is leaving and going to the surroundings. And so this is what we call an exothermic reaction, meaning it's going out. If the sign is positive, that means that thermal energy is coming in from the surroundings, and this would be an endothermic reaction. The other way that a change in internal energy of a system can be expressed is by the work that is being done by the system or the work that is being done on the system. And so if work is being done by the system on the surroundings, again, we're going to have a negative symbol in front of the W piece of this equation. And if work is being done on the system by the surroundings, then we would have a positive value. Fortunately for you, because we are going to be working in systems where pressure is constant, we can assume that work is not being done. So when we talk about changes in the internal energy of a system, we're expecting all of that to happen in the form of heat flowing into or out of the system. So we get to ignore the W component and just assume that delta E is equal to Q. Because in chemistry, when a system does work, it does it by changing volume against a pressure. Since we're working at constant pressure, our work is always going to be zero. So how do we measure heat? We have lots of different units that we use to measure heat. The one we'll use most often is called a joule. This is the SI unit, the Système International unit. And 1 joule is a Newton times a meter, or it's a kilogram times a meter squared per second squared. You're never going to have to convert between joules and newtons or Newton meters. So just accept that the joule is the unit that we use. You'll also hear us talk about calories. You use calories in your everyday life. So calorie is actually the imperial unit. It's the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. And you guys have heard this term calorie before. However, a calorie, the one that you're familiar with, the one that we talk about when we talk about food, is actually a kilocalorie. So it's actually 1,000 calories. So when we talk about a bag of chips contains 100 calories, it actually contains 100,000 calories, not 100. To convert between the two, we know that 1 calorie is equal to 4.18 joules. And as always, if you need that conversion factor, I will give you that conversion factor. And then the third unit that you'll occasionally see used for measuring heat is a BTU, or a British thermal unit. And that's actually the amount of heat that's required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So BTU is much larger than a calorie or a joule. And you might see them in your everyday life, because if you go to purchase a stove or a grill, those are usually measured in terms of BTUs. So it'll tell you that that's a 10,000 BTU burner, and that's what it's measuring. Okay, so when we talk about heat, heat is kind of a tenuous concept, because heat is actually the transfer of thermal energy. It is not itself a thing, but it is a transfer. And so we say that heat or thermal energy flows spontaneously from areas of higher temperature to areas of lower temperature. So heat flows, cold doesn't. So when you talk about something making you cold, you hold a cold glass of water and it makes your hand feel cold. That's because the heat in your hand is actually being transferred to your glass. It's not because the cold is being transferred to you, but that's certainly the way that it feels. So our energy transfer, the amount of energy that's transferred between two objects at different temperatures, depends on three things. One is the nature of the material. So what is it made of? Okay. So certain things transfer energy more easily, certain things transfer energy less easily. You guys are all familiar with your thermo flasks or your Yeti cups. And the reason that they keep your cold drink cold or your hot drink hot is that they have a layer of air, and air does not transfer energy easily. And so we use these insulated cups to try and keep things cold because the nature of that material, the air in between the layers, does not facilitate energy transfer. Of course, the amount of energy transferred also depends on the mass of the material. So it makes, when we think about the definition of temperature, a measurement of kinetic energy of the molecules, if we have more molecules, it takes more energy to make them move. So energy transfer is directly proportional to mass or number of molecules of the material. And then, of course, the amount of energy transferred depends on the size of the temperature change. So a larger temperature change is going to require or give off more energy. So we have these three things: the nature of the material, the mass of the material, and the size of the temperature change. And so the way that we communicate how energy transfer depends on the nature of the material is something we call specific heat. And we abbreviate specific heat as a C with a subscript P. Your textbook actually uses an S. This varies across different texts. We define specific heat as the amount of energy that is required to raise the temperature of exactly 1 gram of that substance by exactly 1 degree Celsius. And as I've said before, some materials have really low specific heats. That means that it doesn't take a lot of energy to raise their temperature. Some materials have really high specific heat, so it takes a lot of energy to raise their temperature by 1 gram. So the size of that value, the specific heat value, is going to tell you how much energy it takes to raise the temperature of that by 1 degree Celsius. So we can use these three things, the nature of the material, the mass of the material, and the size of the temperature change, to calculate how much heat is transferred in a particular temperature change. And so we use this equation Q, where Q is heat, is equal to M, or the mass in grams, times CP, which is specific heat, times delta T, where delta T is the change in temperature. This change in temperature can be in Kelvin or it can be in Celsius, because the change is the same, whether it's in Kelvin or Celsius, because the only difference between the Kelvin scale and the Celsius scale is where 0 is. So when we think about delta T, and we're always going to use delta T as final temperature minus initial temperature. And so whether we start in Kelvin or whether we start in Celsius, that difference is going to be the same. So this is the equation that we can use to calculate the amount of heat transferred when there is a change in temperature of a material. So let's take a look at a couple of practice problems. So our first one refers to the idea that in some areas, solar heated homes, they use large beds of rocks to store heat. So we're told that the specific heat of the rocks is 0.82 joules per gram Kelvin, and it asks us to calculate the quantity of heat absorbed by 50 kilograms of rocks if their temperature increases by 12 degrees Celsius. So I'm going to pause my share here for just a second, and we're going to switch to a different screen so that you guys can see. Oh, let me rotate that around. Okay. So here's our problem. It tells us the specific heat of the rocks is 0.82 joules per gram Kelvin. And it asks us to calculate the quantity of heat absorbed by 50 kilograms of rocks if their temperature increases by 12 degrees Celsius. So the first thing we're going to do is we're going to write our equation, which was Q equals M times CP times delta T. And now over here to the side, I'm going to write down all of the things that I know and what I'm trying to find. So I know that I'm being asked to find the quantity of heat. So Q is the thing I'm looking for. And I know that the mass is 50 kilograms, 50.0 kilograms. And the specific heat is 0.82 joules per gram Kelvin. So the CP equals 0.82 joules per gram Kelvin. And then the temperature increase is 12 degrees Celsius. So delta T is 12.0 degrees Celsius. Now, I can't simply plug all of these things into the equation because I have different units. Here I have kilograms, here I have joules per gram per Kelvin, here I have degrees Celsius. Because this is a change in temperature, 12 degrees Celsius is 12 degrees or 12 kelvins. Whatever the initial temperature in Celsius was plus 273, and whatever the final temperature was in Celsius plus 273. So when we do that subtraction problem, both of those 273s go away. So when we're talking about a change in temperature, Celsius and Kelvin are equal. Now I need to get the mass into grams in order to work with this unit. So I know that there are 1,000 grams in 1 kilogram. And so I'm going to multiply by that, and I'm going to have 50,000 grams. Now, I'm bearing in mind that this has 3 sig figs, this has 2 sig figs, and this has 3 sig figs. So my answer should have 2 significant figures. So now I can plug everything into my equation. And Q equals 50,000 grams times 0.82 joules per gram per Kelvin times 12 Kelvin. And you can see that the Kelvin cancel out, the grams cancel out, and I'm going to be left with an answer in joules. Now, when you plug this into your calculator, it gives you 492,000 joules, but I can only have 2 significant figures. So that's 490,000 joules or 490 kilojoules. So pretty simple and straightforward, starting out by figuring out what I need to know, writing down what I do know, and now just plugging them into the equation. Now, the second part of the question said, what temperature change would these same rocks undergo if they emitted 450 kilojoules of heat? So now I'm going to use the same equation, Q equals M times CP times delta T. But this time I know Q, it's 450, kilojoules. The mass is the same, so 50,000 grams. The specific heat is still the same, so it's 0.82 joules per gram Kelvin. But I'm being asked to find the temperature change. So delta T equals question mark. And again, 2 significant figures, 3 significant figures, 2 significant figures. So my answer can only have 2 significant figures. This 450 kilojoules, I'm going to go ahead and convert to 450,000 joules. And now, once again, I have all the pieces to just plug into my equation. So I have 450,000 joules equals 50,000 grams times 0.82 joules per gram Kelvin times delta T. And I get that delta T is equal to negative, let's back up just a second. Because it emitted 450 kilojoules of heat, my Q needs to have a negative sign here. And so negative symbol there. And that gives me a negative 11 Kelvin. The fact that this is a negative sign tells me that the rocks lost heat, that their temperature went down from whatever it began. Okay, so that's our second question. Our third question asks us to do a little bit more thinking. So our third question says that we have a 245.7 degree sample of metal. Let's see if we can get that to focus in a little bit better. There we go. We have a sample of metal that weighs 245.7 grams, and it's at 75.2 degrees Celsius. And we place it into a beaker containing 115.43 grams of water at 22.6 degrees Celsius. And it tells us that the final temperature of the water and metal are both 34.6 degrees Celsius. So if no heat is lost to the surroundings, what's the specific heat of the metal? So here's our metal, and we're going to take our metal and we're going to put it in the water. So now the metal is a lot hotter than the water. And so the metal is going to cool down and the water is going to warm up. And that's just common sense, right? But what we know from chemistry is that the amount of heat that the metal loses has to be the same as the amount of heat that the water gains. So their temperature changes will not necessarily be the same since we have different masses and we know that they have different specific heats. But the heat that is lost by the metal is equal to the heat that is gained by the water. And so we can say that the Q of the metal is equal to, but opposite in sign of the Q of the water. So it's important that they have opposite signs because one is going to be gaining heat and one is going to be losing heat. So now we can start thinking about plugging into our Q equation. So for the metal, the mass of the metal is equal to 245.7 grams. The CP, or the specific heat of the metal, is what we're trying to find. And the delta T for the metal, the change in temperature for the metal, is final temperature, 34.6 degrees Celsius, minus the initial temperature, which is 75.2 degrees Celsius. And so that's going to give us a negative 40.6 degrees Celsius. The mass of the water, we're told, is 115.43 grams. The specific heat of water is 4.184 joules per gram degree Celsius. And the delta T, or the change in temperature of the water, is 34.6 degrees Celsius minus 22.6 degrees Celsius, which is equal to 12.0 degrees Celsius. So now we have all of the pieces of our heat equations: mass, specific heat, and delta T. And we know that they are equal and opposite. So we're just going to go ahead and plug in all those values. So we have 245.7 grams times the unknown specific heat times negative 40.6 degrees Celsius is equal to negative, and then we have 115.43 grams times 4.184 joules per gram degree Celsius times 12.0 degrees Celsius. And now when we solve all of that, we get that our specific heat is 0.581 joules per gram degree Celsius. And that is the specific heat of our unknown metal. All right. As always, if you have any questions, please let me know. I look forward to seeing you in class.